Professor Daniel Crawford. This lecture will focus on the concepts of angular momentum and space quantization as they are associated with the three-dimensional quantum mechanical rigid rotor problem. The background to this lecture includes a fundamental knowledge of quantum mechanics, including the basic postulates of quantum mechanics, concepts such as linear Hermitian operators, eigenvalues and eigenvectors, quantization in general, as well as concepts such as spherical polar coordinates, and a basic knowledge of the model three-dimensional rigid rotor and its results, including wave functions and energies. But to start with a recap, we do consider this problem within the spherical polar coordinate system, simply because it's much more convenient to deal with than the Cartesian coordinate system. This is typical of any origin-centered problem, like rigid rotation, or for example, the hydrogen atom, or any other atomic system. Within the spherical polar coordinate system, we have three coordinates, of course. We have the radius r, which in general is allowed to range between 0 and infinity, but for the purposes of the rigid rotor problem, we take it to be a constant at some finite value. We also have the colatitude angle theta, which ranges from 0 to pi, and the azimuthal angle phi, which has a domain of 0 to 2 pi. The wave functions arising from the three-dimensional rigid rotor model problem, quantum mechanical problem, are given here. There are two quantum numbers. There's the angular momentum, or total angular momentum quantum number L, which takes on non-negative integer values. And then there's the z component of angular momentum quantum number, typically labeled M, which can take on any value of integers, positive or negative or 0, but it's limited by a maximum absolute value of L. So for example, if L were 2, then the allowed values of M would be 2, 1, 0, minus 1, and minus 2 for a total of 5. The wave functions arising from the three-dimensional rigid rotor problem are outlined here. You have a normalization factor up front, as well as Legendre functions, associated Legendre functions, which are simply polynomials in cosine and sine of the colatitude angle theta, as well as a z component piece, e to the im phi, which is also directly related to the eigenfunctions of the two-dimensional rigid rotor problem, where you only have the single angle phi. Notice again, this is a rigid rotor problem, so r is a constant, and therefore it doesn't appear as part of the wave function. We take that to have a fixed value from the beginning. So the outcome, or output, I should say, from any quantum mechanical problem, includes the wave functions and the energies, whereas the input to the problem is the Hamiltonian. The Hamiltonian, in the case of the rigid rotor, it only contains kinetic energy terms, therefore it only includes a second derivative with respect to theta and phi components. The energies, which are output, depend only on the quantum number L. They do not depend on the quantum number M. They take this form, h bar squared over 2 times the moment of inertia, that's what I is, L times L plus 1. So this is distinct from the two-dimensional rigid rotor problem, which depends simply on the square of the associated quantum number, or say the particle in a box problem, where again the energies depend just on the square of that quantum number. We notice that the energies do not depend on the z component of quantum number M in this case, even though the wave functions do. That means that since I can have multiple possible values of M for a given value of L greater than 0, that means that I have distinct wave functions associated with each of those values of M. That means that, for example, if L equals 2, as we said before, we have allowed M values of 2, 1, 0, minus 1, and minus 2. That means there are 5 distinct wave functions associated with that L, M sub L set of combinations. But all 5 of those wave functions have exactly the same energy because there's only one value of L. That means that all 5 of those wave functions are a degenerate set, and it's 5-fold degeneracy. We also have a total angular momentum associated with our given L value, that is simply h bar times the square root of L times L plus 1. And this is directly related to the fact that the energy, which is entirely kinetic energy in the case of the rigid rotor, could also be written as angular momentum squared divided by 2 times the moment of inertia. So we derive from that h bar root L times L plus 1 for the total angular momentum. Again, only depending on the L quantum number, not M. The other half of this is the z component of angular momentum, j sub z, which has the value of h bar times M. Again, that's reminiscent of the two-dimensional rigid rotor problem, where all the angular momentum was about a z-axis. and all of the angular momentum had the exact same form, h bar times m, in that simpler case. Now let's think a little bit about angular momentum at this point. Angular momentum, when we're thinking about this in either 2 dimensions or in 3 dimensions, it's more useful to think about this in 3 dimensions, we imagine a rotating body in some arbitrarily oriented plane. And that rotating body, when viewed from, say, above, whatever our choice of above is, could either be rotating counterclockwise or clockwise. And angular momentum is a vector describing that rotational motion in this case, 3 dimensions. So it has components along all 3 of the Cartesian axes, x, y, and z, right, where x is coming out of the plane of the board in this case. So let's choose an arbitrary plane for the rotation and draw the resulting vectors. So if I take again my Cartesian axes, x, y, and z, I'm going to draw an arbitrary plane that's just sort of tilted relative to the z-axis. And I'm going to imagine that I have rotation in that plane, again with arbitrary 3-dimensional orientation, rotation that is counterclockwise when viewed from above, which I'm going to define as anywhere in the vicinity of the positive z half of space. Now, I have a radius associated with this rotating body, right? It's a certain distance out, fixed, rigid distance out away from the origin. And because it's rotating counterclockwise, I can imagine a momentum vector, a linear momentum vector. So I'll call r the radius, r with a vector arrow over it, and the corresponding linear momentum p with a vector over it. The angular momentum in this case, which I'm going to call the vector j for consistency with this notation, can be written as r cross p. That's the cross product between the radius vector and the linear momentum vector associated with it. Now, I can write out these things as vectors. So r would simply be a vector with components x times an I unit vector, y times a j unit vector, and z times a k unit vector. Similarly, the linear momentum has components. I'll call them p sub x along the I unit vector, p sub y along the j unit vector, and p sub z on the k unit vector. The cross product for these we can derive from the determinant of a corresponding matrix. So I'm going to write that down here, just to give myself a little room. J, again, the cross product between vector r and p is going to be the determinant of a matrix in which the first row contains my unit vectors I, j, and k. And the subsequent rows have first the elements or components of the left-hand vector of the cross product, so x, y, and z, which are the components of the r vector. And then for p, the third row is p sub x, p sub y, and p sub z. If I expand that determinant, and I'm not going to go through all the details of this, Google is your friend for finding this information, I'm going to find y times p sub z minus z times p sub y times unit vector I, that's my first term in this, and then plus z times p sub x minus x p sub z times the j unit vector, plus finally x times p sub y minus y p sub x times the k unit vector. So these are our new x, y, and z components of my angular momentum vector j. So I could call these, for example, j sub x, j sub y, and j sub z. For angular momentum about the x-axis, about the y-axis, and about the z-axis. Now, this picture so far does not express whether I'm speaking classically or quantum mechanically about angular momentum. So now, to move into the quantum mechanical realm, I'm going to think about all of these components, x, y, z, px, py, pz, as linear Hermitian operators, which they are. If you recall, the linear vector, excuse me, the linear momentum operator involves a derivative, a first derivative with respect to whatever spatial coordinate is associated with it. So let's write that down. So for example, p sub x is negative I times h bar, that's Planck's constant over 2 pi, times d by dx. And because I have 3 dimensions here, I really should write that as partial derivatives of partial x. Similarly, p sub y is negative I h bar partial y, and p sub z is negative I h bar partial z. Those are those 3 components. And the position operators x, y, and z are just simply themselves x, y, and z. I put those 3 operators together with x, y, and z to plug them in to obtain jx, jy, and jz angular momentum operators. Now, it turns out that those 3 operators, jx, jy, and jz, do not commute. That means that their order of application to an arbitrary function in the same space matters. Right? I can't simply switch their ordering. I can get different results. I will get different results. And it turns out that the commutator of these, jx and jy, for example, is I h bar jz. Similarly, the commutator between jy and, jz is I h bar jx. And then the commutator between jz and jx, in that order, is minus IH bar jy. The ordering on those matters. If I switch the order of 2 operators within a commutator, I change the sign of that commutator. Now, I said a little while ago that the Cartesian coordinate system isn't the most useful to be trying to do these sorts of angular momentum problems, especially one that is centered at the origin, like an atom or the rigid rotor is. Instead, we'd rather write these in terms of spherical polar coordinates because they're a bit more convenient. And I can therefore write out jx, jy, and jz in those terms. Now, it turns out that jx is minus I h bar. There's still always minus I h bar up front because that's what carries the units. And then, in spherical polar coordinates, it is sine of phi partial theta, so that's the first derivative operator with respect to the colatitude angle theta, plus a cotangent theta cosine theta times the first derivative with respect to phi. Now that's pretty ugly. Right? That doesn't look like it's convenient for much of anything, right? Well, let's take a look at jy, since we're at it. Jy also has a negative I h bar up front, just like jx and just like jz. But this one is going to have a negative cosine phi, partial theta, so there's a similar structure there, right? Plus a cotangent theta, again, this time sine theta in front of the partial phi. Again, that's pretty ugly. That doesn't seem like it's going to do us really much good at all. Until we finally get to jz. Jz is interesting. That one is simply minus IH bar partial phi. That's it. Very simple. If you go back and take a look at the wave function that I had written up here before, you can remember it's got 2 components to it. There's a theta-dependent piece, which is the associated Legendre polynomials, and then a phi-dependent piece, which is simply e to the im phi, which, if I act jz on that, I will get back simply h bar times the z component of angular momentum quantum number m, right? So again, jz acting on my 3-dimensional rigid rotor wave function, the large beast that I had written on the board before, will give me simply h bar times m times the same wave function. In other words, our wave function is an eigenfunction of the z component angular momentum operator, quite simply. Now, the fact that these 3 operators, jx, jy, and jz, do not commute means that there is an uncertainty principle associated with them. The Heisenberg uncertainty principle always applies to operators that do not commute. And the uncertainty principle says that the uncertainty in what the values associated with one operator multiplied by the uncertainty of the other is always greater than or equal to h bar over 2. There's a minimum uncertainty in both of those observables simultaneously. That means that if I know something about the angular momentum, say about the x-axis, and I have an uncertainty associated with it, let's say I've done a lot of measurements of the angular momentum about the x-axis, and so I have a distribution of values, and therefore there's a standard deviation, therefore there's an uncertainty in that distribution. Then similarly with jy, I have another distribution. The product of the resulting uncertainties must be greater than or equal to h bar over 2. Here's the difficulty. For any given state of the 3D quantum mechanical rigid rotor, every one of my wave functions is an eigenfunction of jz. So therefore, I always have, in the stationary state view, I always have an eigenfunction of jz, which means there is no uncertainty in the value of the z component of angular momentum. And if there is no uncertainty in the z component of angular momentum, there must be infinite uncertainty in both x and y because those do not commute with jz. So let's just say that again. Because I have no uncertainty in the angular momentum about the z-axis, as long as I'm in a state of the 3D rigid rotor, therefore I have infinite uncertainty in the angular momentum about the x and y axes. I know exactly how fast around the z-axis, that is, the projection of my angular momentum vector onto the z-axis, I know exactly what that is, but I have no idea what the orientation is of that angular momentum vector around z, that is, its relative position to the x and y axes. Let's try to visualize this a little bit. I'm going to take the L equals 2 state of the three-dimensional rigid rotor, and we're going to draw out orientations of the plane of the rotation such that it matches the associated quantum numbers. So let's take, again, I'm going to draw my three axes, x, y, and z, just to give us a fixed frame of reference. And I'm going to take the L equals 2 state of the three-dimensional rigid rotor. Now remember, if L is equal to 2, I'm allowed values of the z component angular momentum quantum number m. M can be 2, 1, 0, -1, or -2. So in those cases, I have to draw the orientation of the plane of that rotation such that the total orbital angular momentum value and quantum number is 2, and the z component, that is the projection onto the z-axis, has to have a corresponding value. It's this m that controls the orientation. Now, I'm going to start with the m equals 2, L equals 2. So let's say L equals 2, m equals 2 here. And now I need to draw my rigid rotation in a particular plane such that the length of the angular momentum vector must be h bar times root L times L plus 1, the value that we said of the j quantity before. So I need two things. I need the length of the vector to be h bar root 2 times, L times L plus 1. And then I need the projection of it onto the z-axis to be h bar times 2. So I'm going to put some arbitrary units here on the z-axis. Those are units of h bar, right? Plus 1 h bar, plus 2 h bar, minus 1 h bar, minus 2 h bar. And I want a projection of my vector to match 2 h bar because I'm in the m equals 2 state. And I need the length of this vector, so I need the norm of this j vector to be equal to h bar times root L times L plus 1. And since L is 2 in this case, that's 2 times 3, that is root 6 h bar. That has to be the length of it. Now don't forget, this is just the angular momentum vector. with a positive projection onto the z-axis of 2h bar, which means that the actual rotation in the plane is clockwise about that axis. Now I say it's clockwise. How do I say that? Clockwise when viewed from above, first of all, from the positive z-axis domain. I say it's clockwise because r cross p with a right-hand rule pushes that angular momentum vector upward along with my thumb. Okay? The length of that vector, again, is root 6h bar, and its projection onto the z-axis is 2h bar. Now I just drew a plane here. I picked it arbitrarily just to have the right orientation in space consistent with this schematic diagram. But I don't actually know if this plane is oriented here, right? So the rotation is here, or maybe it's rotated here, right? In both of those cases, I still have counterclockwise rigid rotation, and I still would have a length of a vector that would be root 6h bar, and a projection of the vector onto the z-axis that would be 2h bar. So it matches my L equals 2, M equals 2 quantum combination. But I don't know the orientation of the plane of rotation with respect to either of the x or y axes. That's consistent with what I described about the uncertainty principle before. I know nothing about the orientation of the rotation with respect to x and y. Now what happens then if I choose L equals 2, M equals 1? Let's just put that one right here. I'm going to draw the same thing. Same x, y, and z axes. The length of the vector still must be root 6h bar because, in this case again, I have L equals 2, M equals 1. But the projection onto the z-axis of that vector now has to come down to 1h bar, which simply means that I'm going to reorient the plane so that it tilts a little bit closer to the xy plane, brings my angular momentum vector down. So if here is my unit 1, unit 2 angular momentum, then I want my projection of that vector, j, to be simply 1 times h bar, which means that the angle of rotation, which is perpendicular to that vector, is in a plane that is still counterclockwise, but it's tilted. It's tilted. And now I have the same length of the angular momentum vector, though. The length of j is still root 6h bar. I'm doing my best here to draw these things consistently with length and orientation. It's not perfect. I'm not a perfect artist, so keep that in mind when you're looking at these. So what has changed? The only thing that's changed is that you can think of this as the velocity, if you like it in the classical sense of the rotation, is exactly the same between these two cases. But it's only the orientation of the rotation that's changed. Again, I don't know what it is with respect to the x or y axes. I only know what it is with respect to z. And so if it's m equals 2, I'm tilted up. If it's m equals 1, I'm tilted a little bit more down in this sort of orientation. And you can guess what's going to happen when I get to m equals 0. Let's draw that. For m equals 0, now where's my angular momentum vector going to be? Now I need a 0 projection onto the z-axis, which means the angular momentum vector must be in the xy plane. So I'm simply going to point it along the y-axis arbitrarily, which means that the rotation contains the z-axis. But from this point of view, that is from the positive y direction, I've now got a counterclockwise rotation. I still don't know the orientation with respect to x and y. I just picked one here to draw it. It could be in any orientation, right? Any position relative to x and y, because I know exactly what the orientation is for z. Now the projection onto the z-axis, j sub z, is 0, but the length of the j vector remains 6h bar, root 6h bar, just as it was for these other two cases. So again, this was for the L equals 2, M equals 0 case, okay? Projection onto the z-axis of the angular momentum vector is 0. And the last one I want to look at again is going to be minus 1, because we learn a little something new from going to negative numbers. X, Y, Z again. Everything's the same as here, except that now I'm pointing my angular momentum vector below the plane because I need the projection of it to be negative h bar, corresponding to L equals 2, M equals minus 1. So again, the length of the vector, J, is still root 6 h bar, but its projection onto the z-axis is now negative h bar, that is negative 1 because that's the value of m. So where is my plane of rotation? It's still perpendicular to that, which means I could turn my head upside down and draw it like so, and from the perspective of that vector, it's clockwise. But if I'm consistent with my perspective from the others, particularly for positive 1 and 2 values of m, if I view that from above, that's now clockwise, not counterclockwise. Right, so again, there's my plane, there's my rotation, right? When I'm viewing it from the perspective of the angular momentum vector, it's counterclockwise. But if I look above, that's a clockwise rotation. That's what the negative values correspond to. After you move below the plane in these two cases, if you continue to view the rotation from above, you simply reverse the direction. Exactly the same speed and the same orientation relative to the z-axis. We call this all space quantization because my quantum mechanical rigid rotor cannot just be oriented anywhere in space, right? It can be oriented anywhere in space with respect to the x and y axes because, again, I know nothing about their position for those. But relative to the z-axis, our special axis in spherical coordinates, the orientation is fixed depending on which m state, that is z component of angular momentum quantum number, that I'm in. The speed is the same in all of these cases because I've got the same total angular momentum quantum number, but the orientation is different. I can't have an orientation in which J falls somewhere in between this 2h bar projection and this 1h bar projection. In these stationary states, the eigenfunctions of the Hamiltonian, that's simply not allowed. It can't physically occur. So I hope this has given you a basic overview of angular momentum, some of the fundamental concepts, particularly as it relates to the rigid rotor, but also this concept of space quantization and the idea that our rotation must occur with fixed orientations relative to our chosen special z-axis. Thank you very much. I hope you found this to be useful.